questions on what we went through with Unit 1 stuff? All the Part 1 study guide. We good with everything there? You hope so? There's a lot of stuff that comes in that from that point. So, I mean, we already talked about this today, right? Yep, that makes sense. You're like, oh, that was it right there, Brother Bowden. Right there, that very information. I wish I'd known that 3 minutes ago. Yeah. Someone came in this morning, to be left unnamed, but asked a good question. They said, I want to go ahead and show you what I'm doing with the chymotrypsin mechanism, and proceed to draw it up on the board. And the first thing they said was, I'm going to take these electrons as my first step and attack this carbonyl. Why is that not true? That's, even though that's written in this first step, why is that not true? Okay. Kevin?
Well, it's important to understand that the only reason this reaction is happening is because the pH changes on the histidine nitrogen.
Yeah, the pKa's change.
Which causes the histidine, the nitrogen on the histidine to protonate and take the hydrogen from the serine. That's what starts this reaction.
So this reaction is started when this lone pair gets, this nitrogen gets really greedy on this amino acid. And why did this change its characteristic from where it was at in the native protein? Yeah.
So it's because it's interacting with aspartate 102.
Okay.
And this is something I wanted to confirm. So when the enzyme binds, does that cause a conformational shift so that they can start to interact now?
Okay, now
So what happens is when the aromatic portion of the molecule goes into the cytophobic chain, that's what causes the histidine to move up and interact with the aspartate.
so binding of the substrate's aromatic amino acid into that causes a conformational change, which then pushes the histidine aspartate close enough together that that hydrogen bonding event occurs, which changes the pKa on this bad boy right here, causing it to attack the serine. If that were not the case, what would be the fate of the serine?
It would never attack. It's not an electrophile or a nucleophile.
It would always be done, or it wouldn't do it at all.
Yeah.
Right? It would always be stealing that proton. And once protonated, even if it got reprotonated by some passing water, it would always, it would kill itself, right?
Yeah.
So this is only hungry when this is occupied.
Cool.
Otherwise, it's no good to us. Okay?
And you just pointed at this. Those
Meaning this histidine, this nitrogen on it, is really hungry for the proton. And it's, what do we call this when the electrons here remove this proton? Tell your neighbor, what do I call that? If you said, hey, a deprotonation event, is that fair? Sure. Acid-base chemistry, sure. Could I abstract a proton? Sure. What else did I say? Is this a nucleophilic or electrophilic attack?
Electrophilic.
Which one's the nucleophile, which one's the electrophile?
The electrophile is the nitrogen, or the nucleophile is the nitrogen.
The one that loves the electrons is the, which one? It's really removing, right? The electrons are attaching to the proton, so they become the ones that are loving the proton. But it's kind of a funny way to look at it, because the electrons are staying where?
With the
nitrogen. But, yeah. Okay. So, go ahead. Yeah, you totally call it, but this is the.
That's awesome.
Electrophile, right? There's your nucleophile. And we say and this is how I always describe it, a nucleophilic attack, right?
So the chymotrypsin mechanism only occurs when the aromatic ring is present.
Yeah, that's correct. Yeah, which makes perfect sense. Otherwise, the chymotrypsin would always have deprotonated the serine, but then the serine would be reprotonated by water and it wouldn't ever do anything.
We're just gonna gain,
Okay,
which is hydrogen.
all right.
So it's going.
So that's the first step in this. Where do I want electron? Let's get the nitpicky part. You started memorizing this and you realized some things. Do I care if there's a lone pair here?
Yes.
Yes.
Yeah, I want you to draw the lone pair. Why? Because if you draw this arrow and you're drawing it from the nitrogen to the hydrogen, what are you telling me without the lone pair?
It's a
That nitrogen, the atom, the positive atom core, just went and grabbed the positive atom core of a proton and said, let's do fusion. Hans and Fleischmann have nothing on you guys, right? I mean, that is like, no, I'm not saying that. Cold fusion is not happening here. Okay. These electrons, somebody asked me a good question today as well. I am okay if you draw, just like the textbooks here, these electrons going from the bond to the carbonyl, the backside of the carbonyl. That is just fine. Some of you will say, but when I was doing OChem, we would have said that these electrons fall back to this oxygen, and I would be taking one of now the existing 3 pairs of now electrons, of lone pairs, and be attacking the carbonyl. One is shorthand, one is longhand. Why would they be doing the shorthand? Is it because they don't know the longhand?
less arrows.
It's a lot of stuff to draw. They're trying to fill it in with less space. I am okay though if you choose to just draw some lone pairs and say it's going back to the nucleus here, and I'm going to draw some lone pair on my oxygen here. I'm going to go to the carbonyl.
Cool.
That's probably a much cleaner way. Yeah.
They also, these illustrations show the negative on the oxygen that's moving around and reforming bonds. Is that?
Yeah,
is
so
that
good
implies-
point. So then these electrons come here and they're coming to the oxygen, which makes perfect sense. That's the most electronegative species. How fast do electrons move, by the way?
Very
Light.
fast.
Fast, about 10% the speed of light. So how small of an area is this?
We're dealing with
It's an
exponential-
electron cloud. Is that okay to just say it's just they're there and they're just moving super fast?
Yes.
Right? I mean, it's harder to. Why are we calling it a cloud? Because it's just there. It's like moving way too fast. Then we learned about the Heisenberg uncertainty principle. When we looked at what did it do, it changed the whole thing. Right? Yeah, I know. Okay. You didn't learn the Heisenberg uncertainty principle? You'll hit go. What would happen to an electron if I tried to look at it with light? Would it change the electron's behavior?
Yes.
What would happen if I tried to run it into a piece of film?
That changes behavior too.
What would happen if I tried to pass it through a voltage gate it changes? Anything we do to look at it, we're changing the electron behavior. So when we looked at it, we messed up. By the way, there was a recent publication where they just showed, within this last week, that they could actually now selectively decide which of the two possible fates it would go to. I'm waiting to dig into that. Sorry, I'm working on your corrections and other corrections. In the meantime, my good science is happening out in the universe, right? All right. It's where you're at too. I'm like, I'm learning a mechanism. I don't know, what are you at? The next question that Natalie asked is they draw this as a negative. Okay. You could technically be drawing 3 sets of lone pairs there. That implies the negative charge as well. It is typically drawn with the negative charge. Why does this one have 1 hydrogen bonding and this one has 2? Go for it, Chris.
Yeah, just because the pi bond is getting, you're getting rid of the pi bond and the electrons are being put on the outside, and it's just more electronegative, and it's able to.
And it's occupying more space, it's more electronegative. It definitely has more of that formal charge. Yep. So all those answers are correct, which means that it's actually looking for more. This is a stabilization event of the intermediate. This is the transition state we're stabilizing, right here. Right before what happens here. I'm cleaving this bond, so these electrons come up here, and then I actually take these and extract the proton, right? Now, once this happens, I was at this high activation energy, now I'm going down the other side, okay? That's really what you're looking at.
To confirm, we're doing the same shorthand, where technically those electrons are going to the nitrogen, and then from the nitrogen to the proton.
Yep.
Okay.
Yep. Now, do I have to write histidine 57?
Yes.
Yes.
Is it good to draw the one carbon here and then the histidine shell? Yeah, it is. What is this bound to? Aspartate 102. And should you draw that for me?
Yes.
I asked you to draw it every time. What do I draw on the aspartate 102? Do I have to draw the whole aspartate?
Well, just the R group.
Just the R group's enough right here. It's telling me that you know what it's actually interacting with when it's hydrogen bonding. Is this better than just a regular random hydrogen bonding? Yeah, because that's a carboxylate group, right? Okay. So show me those elements. You're essentially recreating exactly what's drawn here. It's not a problem, okay? What's wrong here? Tell me. What's wrong? What is wrong here with this nitrogen? I left it this way on purpose so that I'm forced to do something. What is wrong with it? I'm doing what? Cold fusion. I'm saying the nitrogen's attacking that proton. That is awesome. Man, what a sloppy textbook notes there. Yeah, I just got the textbook notes. I'm not the creator of these. Just fix it, right? So there should be a lone pair there.
Cool.
Okay. Oh man, I didn't. Now you say it, I guess I knew that. Because I knew it 2 seconds before. Okay. Okay. Anything else there? You guys good? Yeah.
As far as the last box on that test, the step 6, essentially, it's the products of in the actual enzyme, like the enzyme we created, correct?
Right. So this one right here, is it now attached at all? I mean, you're sitting
It's
now,
the hydrogen bond.
but this is really ready to leave.
Yeah.
Right.
I just wanted to make sure, because I guess enzyme product, we would just sound like this is what you want the product to be, but that makes
Yeah.
sense to
What I'm really looking for is the empty pocket, kind of, essentially the final product ready to leave. So I would draw it just like this, and I just draw the arrow of it leaving. Because I'm trying to cut one step out. One step which coincidentally, based on what I said, this right here and this interaction here and this ready to extract the proton, yeah, it's probably hydrogen bonding, but it's not really pushed that close until last minute. Okay. Well, okay. Feeling good about your chymotrypsin mechanism? This is cool. It explains a lot of things. Did I need to learn this one?
No.
No. Hexokinase though, is it metal ion catalysis?
No.
No or yes?
No.
Tell your neighbor, commit to something.
I want to say it's general acid base catalysis. That's what it says.
Hexokinase doesn't have
the manganese because the carbon.
Okay, there's definitely a metal involved, right? In fact, the metal has to be there or the reaction doesn't happen, but it turns out, is the metal on the enzyme or is it on the substrate?
Substrate.
That's the difference. If it's involved where it's on the enzyme and thus it's stabilizing the transition state in the with the substrate, that's different than the other way around. So this is just general acid base. What did this one have in it? Covalent catalysis and
Acid
acid base. So can it have more than one?
Yes.
Could it have all three?
Yeah.
It could. It could have all three. It could have, this one has two. Tell somebody else how you know that one had covalent catalysis. When did it have covalent catalysis?
And when it gets released.
You're forming a transient covalent bond that sticks around with, like, it's covalently bonded during the intermediate, but then it exchanges the covalent bond after
The other one, I just had
the water.
Okay, so here it's got a tetrahydral, it's got an intermediate, right? And so, gosh, it's right here, but what is it about this? It's nothing to do with the tetrahydral. It's this step has what? A covalent bond between the substrate and the enzyme. If that forms, then we're there. But that tetrahedral intermediate, that is an important part, but that's not always the case. Hence, when we get down here to this one here, does it also have a tetrahydral intermediate step?
Yes.
But is it got covalent catalysis?
No.
But is it acid base?
Yes.
Yes. Is it metal ion catalysis?
No.
No. Okay. You guys are sharp at this game. Any questions with this one? I feel like I learned that I got it. It's golden. My life is good. We left right here. This one is metal ion catalysis. It's the one I wanted to introduce as your example. It's the one that's in the textbook. It's actually not my favorite one. Really. I'm just showing it because it's out of the textbook. 2-phosphoglycerate going to phosphoenolpyruvate with the enzyme known as enolase. Enolase is part of what? Glycolysis. Man, they're starting to teach you glycolysis right now. You just didn't know it. Okay? The enzyme has these two magnesiums hanging out on it. Cool. Well, now that these enzymes are there, what is it doing when it's, I've got this lysine group, this glutamate group, nucleophilic attack, abstracting the protons, these electrons fall back into this. Whoa, that's cool. Too many electrons here, but wait, is this how am I getting these in here? I'm adding a lot of electrons down here. Is this normal?
It can happen.
I've got, oxygens all around this, electrons all around this. That's negative, that's stabilized as an intermediate because I have the
Magnesium.
So it's facilitating this opportunity. Okay? Yeah, the electrons come out and then we fall back. It's not really stable. Well, maybe we can move it over here, which we do. PEP is a little bit stabler over here. And there we go. And water comes off. Life is good for us. You have to memorize that.
No.
Is there any acid-base chemistry going on there?
Yes.
Is there a covalent catalysis strategy going on there?
No.
Boy, you guys are good at this.
I mean, is it fair to assume that it's probably going to be acid base? Because
In most instances, you're going to see acid base. Why?
because it's really common.
Super common. Yeah.
I think on the study guide, there was a question about, looking for an example of specific acid-base catalysis, but I couldn't find one, so am I just missing it, or?
You're seeing it in everything.
Okay.
Every example they're giving you is doing acid-base catalysis.
I mean specific versus general.
Specific what?
Specific versus general.
Oh, versus general?
Yeah, it just seemed like everything was general.
Yeah, just general.
Okay.
Yep. I don't know, that's probably sloppy use of the term. All right. So, this is another use of it in this case, I've got nickel. This is urease. Urease is known to break down what molecule? Do you guys know what it's breaking down? What is this bad boy? That's urea. What do we use urea for in biochemistry?
It's a reducing agent, right?
It's like denatured.
Denaturant, right? We use that to denature things. We talked about that in Anafitzin's experiment with the ribonuclease reductase. Okay, so SDS works, urea works, guanidinium hydrochloride. Urea was the first molecule we synthesized that let us know that the atoms themselves could indeed be turned in from our dirt, could be turned into real biological molecules. We know that, we easily accept that today, but we can also break it down. Nickel is used in us as well as in plants. In fact, in plants, it's the only case we see nickel used. Is nickel usually considered helpful, or is it one of the metals that you'd say you should take lots of that into your diet?
Probably not, but I'm aware of it.
No, but it uses it for this enzyme, which breaks down urea. Okay? You produce urea as part of breaking down your nucleotides and amino acids to get rid of your nitrogen so that your blood pH doesn't go up. Okay. So there it's just coordinating with the urea, and there's a whole awesome mechanism, and again, you don't need to learn it, but what I'm trying to show you here is there's lots of other examples of, yeah, you don't have to answer all those questions, they're cool, but you don't have to answer them. But I did want to spend some time here, because this is in the textbook, and this is valuable. Bacterial cell walls made of peptidoglycans, you all know that, I hope, except for those who are chemistry majors who are like, what? I never knew that. Okay, we talked about peptidoglycan layers. Those coat what? Just gram positive or gram negative?
Both of them.
Both, but one has what on top?
An additional.
Another membrane layer on top. Okay, so, all right, so peptidoglycan layer is created in these bacteria, and that allows them to hold their pressure. So if I put them into water, the bacteria have salt in them. What's the bacteria going to want to do? Suck it all up till it blows up. But they don't. That's because they've got this peptidoglycan layer hanging out on it, okay? And so that's protecting it. So what happened is it does this cross-linking event, and there's this cool event that happens. I've got these two amino acids. What amino acid is that? Alanine. What's unusual about these
They're
two?
D instead of L.
They're both D. Wait. I thought we never used D. No, we use D. Just rare. Okay, bacteria here. This transpeptidase has a serine on it. Huh. Looks familiar. This base abstracts the proton here, which then allows these electrons to attack the backside of this carbonyl, which then break this bond right here. Wait. Is this possibly a serine protease?
Yep.
Yes, it is. This is a serine protease. The transpeptidase enzyme that bacteria are using is a serine protease. It's worked specifically to attack the alanines that recognize moieties. Why is this valuable? Because once it does that, it creates the peptidoglycan layer, okay? Finishes the reaction, yep, comes back in, and then cleaves off the enzyme so it can leave, and so we start doing that. This is acid-base and covalent catalysis,
Sorry.
just like the serine protease, yes.
And that this is how the peptidoglycan layer is formed.
It's created,
Okay.
okay? Aha moments of reality and Brother Bowden tangents. Life expectancy, 770, okay, to 2021. Yeah, and then what do we got going on here? Oh, that's COVID, don't worry about that stuff. That's what some people said.
Yeah.
We can make a dip in the world's population. You're like, well, maybe it wasn't so bad. Yeah, it's pretty good. Okay. So what is it that allowed this to happen? We're going on at like 35, and then what's happening here that allows life expectancy to start climbing?
Penicillin.
Medicine.
Antibiotics.
Specifically what? Antibiotics, yeah. So 35 to 40 prior to 1880s, poverty and malnutrition, the major facets. Infectious disease killing perhaps 1/2 of all children born prior to adulthood. Antibiotics become the biggest contributor to increased lifespan. First use of penicillin, 1942. So we're talking these right here. This is all we started feeding you. And anything beyond that is where? Antibiotics. We're keeping you alive because, so a lot of us, when we go to the doctor, are really happy because the doctor's going to be able to treat our cancer or be able to give us a heart transplant, be able to do some awesome surgery. I'm gonna be honest, we're barbarians. We don't have hardly anything figured out. God is revealing knowledge, but we are barbarians. The real increase to your lifespan, a very small fraction, is because of what we do in the surgery room. Mostly it's due to what? Antibiotics. And the doctor who did bother to go carve you up, what does he do? Washes his hands.
Yeah.
Now, I'm not trying to shoot medicine in the foot. I'm just telling you what's the big deal is that we're losing that battle. You've heard of antibiotic resistance. We're losing this battle. What will happen if we lose it? Doctors, lifespan of 50. Everybody's going down. Whoa! We gotta win this battle. Where's that gonna be fought? Biochemistry, enzyme kinetics.
Oh no.
We gotta know this stuff. Oh man!
Oh no.
Like, what could I be to contribute to the world to change it? Solve the problem. Okay, let's see what we got going on. Dealanine substrate looks a lot like what? Penicillin. This is the beta-lactam ring. Turns out that this looks like this. We confuse it with what we're looking at. So the enzyme itself comes in here with the beta-lactam ring, and the transpeptidase we just learned about, serine protease, attacks. Ooh, nice. Abstract the proton, come in here, and I can't get it off.
Nice.
Dead end intermediate. Beautiful. That is not antibiotic resistance. That's what Fleming discovered, okay? Cool. Nice. He didn't know what he discovered, but that's what he did. Here's the problem. Yeah. Antibiotic resistance. Beta-lactaminase comes in. What does it do to penicillin? When I get this new enzyme called beta-lactaminase.
It acts the same.
It attaches to it, but what is it capable of doing? It leaves. It's capable of leaving. Ooh. Then what did I do to all my penicillin?
Consumed.
It's all dead. So that means that if that's all dead, what can this do now?
Keep going with this.
It can keep going, and that means I got a problem. Okay, so there is a new enzyme that's been mutated that now can take care of taking out that beta-lactam. And most of our antibiotics are based on that mentality. So we counter. What do we counter with? Let's see if we can take out the beta-lactaminase. Let's redesign our clavic acid. And in so doing, because of the way we built our ring structure, we are able to stick it back to beta-lactaminase. Awesome, we gotcha. Then they mutate again.
And we're like, freaking A.
Yeah. So, without showing you what I could show you, which I probably should show you in the last minute. Let's see, where did I stick that? I'll show it to you later because I know where we're at in time. There's another whole avenue we are now attacking all the prokaryotes. So it's totally different mentality, and it's an antibiotic.